Okay, good morning or afternoon or whenever you're watching this. Haven't done a video for a little while here. Thought I'd give you guys a rundown on voltmeter, analog voltmeter calculations and how we go about doing those. We will be going through these in the virtual classroom, but those of you who like to have a review, quick little mini lesson here, you can watch this at your leisure, I guess. So principles of a voltmeter. Any type of voltmeter, we need to make sure that we are connecting them in parallel. And the reason for that is they have a high amount of resistance. So if we were to put them in series, what we end up doing is something called meter loading, or we alter the way that the circuit is designed to operate. If I had an original circuit with a couple resistors in it, okay, and let's say I have 120 volts here, and let's say each of these resistors are, say, 50 ohms, okay? Without doing any significant math, we would know right away that if I placed my voltmeter, whoops, that's not a good working pen. If I placed my voltmeter in parallel across that, I would anticipate to read 60 volts, okay? And I would also anticipate to read 60 volts here. However, if I made a mistake and installed my voltmeter in series with that circuit, because of the amount of resistance internally in that voltmeter, we would then add a significant amount of resistance to this circuit, which would then alter the original circuit current. So the voltmeter would see a significant amount of voltage drop across it because it has a much higher resistance than either of those two. All right, so that is something that we definitely never do. We do not connect up a voltmeter in series. We put it in parallel like I've drawn up here. Now, if we focus just simply on a voltmeter and its design, and when I say a voltmeter, an analog voltmeter, and its design, and let's pretend that we are just going to focus on that resistance that I just drew there. So this was that 50 ohm resistor that was connected up to that 120 volt circuit over here, okay? So I'm just going to draw briefly the rest of it at the bottom here. So this was the other 50 ohm resistor, okay? But we're going to focus on connecting up our our voltmeter in parallel with that circuit. Now, if I just put my analog coil in parallel with that, there is a limitation to the amount of current that we are capable of having that coil handle. Most coil resistances in your booklet, they either say they're 50 to 100 ohms. I'm going to stick with an easy 100 ohm resistance there, okay? The problem with this circumstance, and actually what I'm going to do is I'm just going to change this guy down to 100 volts, make our math a bit easier. Okay, so if this is 100 volts there, I anticipate that voltmeter to read 50 volts here and 50 volts here. Okay, and my circuit current before that meter went in would have originally been 1 amp. But we know that this meter is not capable of handling anything greater than probably 50 milliamps. So what we need to make sure is that we install some sort of protection in series with that coil in order to limit the amount of current that coil is going to see. Okay? We call this resistor here our current limiting resistor, okay, or our multiplier resistor. All right, so that's an important component that we need to look at. If we're going to put a subscript here, we would use Rm, okay? This becomes Rc, or I guess we should say that Rc is 100 ohms, okay? We need to solve for Rm, and it's important for us to know is the amount of current that this guy is allowed to handle safely. So we're going to stick with their rating of no greater than 50 milliamps, and we're going to label it FSD, which equals full scale deflection. Okay? Now, we also need a range. We need a range for this meter to be capable of handling. So we're going to say that this is a 0 to 100 volt voltmeter. That's the range. So at full scale deflection, in other words 50 milliamps, it would be capable of handling a voltage potential of 100 volts if it was to be put across it. The bulk of that voltage drop would be across here, minimal amount there. Okay? So, where do we go from here? In order for us to do a calculation, neglecting any of this information now, it really doesn't matter what's happening here, because we're just going to focus on what I gave you there. So I'm just going to get rid of all of this. Okay? And we're going to do a calculation to solve for the multiplier resistor. So if I'm at a 0 to 100 volt setting, and I've got 50 milliamps of full scale deflection, what would my R total for the circuit be? Okay, so my R total is my E total divided by my I total. This is very similar because this circuit here is just a series circuit. So we're going to go 100 volts divided by 50 milliamps. And what does that give us? I'll take my calculator out to make sure that I do this correctly on film. 100 divided by 0.05. That gives me 2,000 ohms. So that's the total resistance of this voltmeter. Okay? Now I can subtract my coil resistance of 100 ohms minus 100 ohms. And that will give me my RM, or my multiplier resistor, okay? And that in this case is going to be 1900 ohms. All right? Significantly greater than what this 50 ohm resistor was here. Remember, current takes the path of least resistance. Bulk of the circuit current is going to go through there, okay? Leaving just enough current to be able to go through that meter there. In this case, the amount of current flowing through here based on the circuit that we had connected up to it would not be 50 milliamps. It would actually be 50% of that, or 25 milliamps, in order for this meter to actually be reading 50 volts. Okay? So that's a basic calculation for a multiplier resistor. We need to know what the full scale deflection current would be. We need to know the coil resistance, and we also need to know the voltmeter range. Okay? If we know all three of those, then we're good to go. Okay? So that's the simple calculation on how to solve a voltmeter. All right?